Okay, hello everyone. We're in the next section now. So, like we said, the last section had a lot of kind of random topics thrown into one. Well, I mean, they weren't random. It was all function type stuff, but these next couple sections get more specific, but I think different parts of the previous section will help in this section. So this section is more talking about the graphs of functions, which we saw a little bit in the previous section. But okay, what does it say here? It says, can I really tell that from a graph? Graphs provide a visual representation of how functions change over time. Which, if you see, I guess like in economics classes or different science classes, and I don't know, you might see graphs that represent things that in real life. And this section I think will really help for those types of things. Many characteristics of a function are much more evident from the function's graph than from the equation that defines the function. So it's true, sometimes a visual really helps, you know what I mean? Like, if you're reading about something, even if it's not math, I don't know, you might be confused or you can't picture what they're saying, but if they provide a visual kind of, and I don't even know exactly what we're talking about, but sometimes that helps a lot. So that's kind of the idea, I guess, for graphs especially. We can use graphs to determine for what years the fuel efficiency of cars was increasing and decreasing, for example, and then at what age men and women attained their maximum % body fat. That's interesting. A graph can even help you understand your cell phone bill better. Yeah, that's fair. Unfortunately, I don't want to think about that, huh? Let's see. What do we start with here? Okay, so yeah, the first topic here is talking about intervals of increase and decrease. So one thing I'd like to point out before we even start is, like, if you look at this first graph, the one on the top left here, I'm going to kind of color it in blue. It goes wee like that. So imagine, I guess it depends what part of the world you're from. Like we read from left to right. So I might look at this graph and I'd say, okay, from left to right away it starts increasing. So it's almost like if I were going this way, I'd be going up a roller coaster, upward, so it's like it's increasing. But once I get to this hill, the top of this hill, it's like it decreases. It goes whee, and then when it gets to the bottom of this little valley, it starts increasing again and up and up and up. So that's true. But then I think if I remember right, in Japan they read from right to left. So then it'd be the opposite. It would look like it was decreasing until it gets to here, and then it looks like it's increasing until it gets to here, and then it looks like it's decreasing, which is the opposite of what we just said. So what we want to keep in mind is, like it says here, when we start at the left and follow along the graph, at first the graph is going up, and like blah, 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 blah. But we always read these graphs from left to right. So if you're looking from right to left, you're doing it wrong. And actually, I'm not sure if is that how it is everywhere? Like in Japan, when they talk about intervals of increase and decrease in math, are they looking from right to left? Ooh, that's a good question. Oh, well. So, okay. So notice that it says, at first the graph is going up. This continues until x equals -1. The function is increasing on the interval. So I guess you're like thinking, when does it start increasing? Well, it looks like, since there's an arrow going downwards, it looks like it's going down forever. So it's always increasing going that way. So it's not like a roller coaster that has a starting point. It's just increasing from -infinity, which is, down forever, up until this value here, because that's like the high point of the graph. And when we talk about intervals of increase and decrease, we always talk about x values. So you're never going to specify y values. We're actually not even going to look at the y-axis. It only goes up to an x value of, and that's tough to look at. I'm looking at this guy. I see that this is a 5. So what does it look like the high point here is? This one I think you could just kind of guesstimate. I think to me it looks like it's maybe 2? I don't know, something like that. This is just kind of for practice. So if you said 1 or 3 or whatever, then I think that's fine. This is just more for practice. The problems I would give you on an exam or on the homework or quiz, those will be more obvious and precise. So interval-wise, like we already put a parenthesis next to infinity, but what do we put next to 2? I'm going to put a bracket next to 2, as we talked about in the previous video, because there is a point at x equals 2. Or I'm guessing that's what it is, x equals 2. It kind of looks like that. Wait, dang it. You guys, did I just go against my own, what I just said? Oh my gosh. Oh, I'm losing my mind. I'm sorry. I had just said that when we're doing this, we're looking at x values only. Oh my gosh. We're looking at x values. So it's going, it does go from negative infinity because we're looking at x. This goes to the left forever because this graph, it goes, where is he? The arrow's going down. I mean, it's not only going downward, but it's going left forever. So the interval of increase goes from negative infinity because presumably it's increasing forever downward. And that doesn't make sense. And then it stops increasing at, and I was looking at the y value, exactly what I told you not to do. I was trying to line it up with the y-axis, but I want to line it up with the x-axis. So you're only looking at these numbers on this axis, not the ones that are counting by 5, 10, 15, 20. Those don't even matter anyway. Oh my gosh, I'm crazy. Sorry, so that high point, that like the top of the hill, you know, on the roller coaster, it lines up with -1 on the x-axis. I was looking at the y-axis. Come on. Well, hopefully my mistake will help you not make that mistake. When you're taking the test, you're going to say, I'm not going to be a silly person and do like she did. Sheesh. And then it says, okay, but then at x equals -1, the graph turns and moves downward until we get to x equals 1. The function is decreasing. Oh, shoot. Parentheses here on the interval -1 to 1. So it's only decreasing for a little while. Let's see. Do we have any colors left? Yeah, so like if it gets to this high point and then it starts going downward up until there. Okay, and then I'm gonna talk more about parentheses. So just I guess by convention and just by everybody agreed to do this, intervals of increase or decrease. Intervals of increase, like the one we saw here, or decrease, like the one that's directly to our left, always have parentheses. Never brackets. So, I mean, in the previous section, we looked at brackets and parentheses and we had to decide which one is it. But that was because we weren't referring to intervals of increase and decrease. When we're talking about intervals of increase and decrease, we never include I guess the idea is the values where it changes from increase to decrease. So, for example, like this high point right here, you know, right at that value, it's not really increasing or decreasing. Because if he looks to his left, he sees increasing, but if he looks to his right, he sees decreasing. So right at that moment, it's neither increasing or decreasing. It's like a inflection point, they call it, where it's changing from one to another. So I think that's why you never include those values where it changes from one to another, because, yeah, like if I were to put here, like in the interval of increase, if I put -infinity to -1 including, that means at -1, it's actually increasing. But it's not really, because it's kind of increasing and decreasing at the same time, depending if he's looking to his left or to his right. So just, yeah, like I said, kind of by convention, we never use brackets, only parentheses. That is when we're talking about intervals of increase and decrease. Okay, and then it says, at x equals 1, the graph turns again and continues in an upward direction. So it goes from 1 to infinity, and that's an interval of increase again. So that was this last part. It's like from here up. Yeah, so it's increasing on the left side, it's increasing on the right side. In the middle, it's decreasing. Let's try another one. Now, this time they're not going to guide us through it. We're kind of on our own. So let's see, what do we have? This guy's a little simpler looking, which is nice. Like, so remember, like we said, we're always looking from left to right. So if I look at the very left of this graph, and I go to the right, is this increasing or decreasing? Well, if I'm going from left to right, I'm going down. So it's decrease. Let's see. So I'll write interval. Interval of decrease. There could be more than one. There could be just one. This one happens to only have one. It's going to the left forever, so it goes from -infinity. And the x value that it stops decreasing at is this kind of low point here, and I'm going to line that up with the x-axis. It's at -1. And like we said, you don't even have to think about it. Intervals of increase and decrease are always parentheses. And then we'll look at interval of increase. It looks like from there, from that low point, right here, then it starts increasing. If I'm looking from left to right, so from the very left guy to the right, it's increasing, and it's increasing forever. So starting at an x value of -1, going off to infinity to the right, that's an interval of increase. So that one was a little simpler. It's the ones that have multiple intervals of increase, multiple intervals of decrease that are kind of tough. Okay, so like I said, that's just yet another thing to memorize in math, that There's no such thing as intervals of increase and decrease that have brackets. It's always parentheses. So, okay, what are they asking here? Let's say it's two part A says, look at the graph and solve problem number 1. Okay. Locate values at which the function f has any relative maxima or minima. What are these relative maxima or minima? Okay. Well, we haven't even talked about that yet, so we're going to define it here. It says, okay, relative maximum occurs where the function changes from increasing to decreasing, and the relative minimum occurs when the graph changes from decreasing to increasing. Or in other words, a relative maximum is kind of what you think. It would be the top of a hill. That's how I think of it, a hill. And then a relative minimum is like the bottom of a valley. A valley, or like a low point, you know? This is like a low point, and this is a high point. Yeah. And then we have yet another thing to kind of memorize here. It's kind of unfortunate, because if they say, okay, what is the relative maxima or minima? Let me look back at that graph. Well, there was the top of the hill. It occurred right here, and I don't know. This is where, like we said, we're kind of guessing that happened at a y value of 2. I think was my guess. I don't know, but x equals -1, y equals 2 was a maxima. Oops, maxima. And then the other, the valley, I guess we could say, where was it? This guy. That occurred at, oh man, I drew over it so much I can't even tell. I think it looks like, to me, it's, like I said, the y values are kind of hard to tell, so it's kind of up to you. But I see an x value of 1 and a y value of maybe -2 or negative something. X equals +1, y equals -2, maybe. But when they ask what is the relative maxima, what is the relative minima, they actually want the y value, which is super confusing because usually they want the x value. So I'm going to say a relative max occurs at 2, so you specify the y value, when x equals -1. So like, I guess when they say relative max, they want to know exactly how high is that max. And then relative min, exactly how low. So I think they want to know how high or how low. That's why they want the y value. Relative min occurs at, okay, what was that low point? -2? That's my guess anyway. It was hard to tell when, and the x value was +1 there. Let's try that for this other guy. That's an interesting looking guy. Looks like a butt. Okay, sorry. Too much. Going too far with it. All right, let's see, it looks like it has, I guess it depends what you want to look at first. Relative, I don't know, max. I'm a positive person, you know, look at the highs first. So I think there's only one relative max because there's only one hill. I wouldn't count this guy because it's not like a hill, you know, you need it to be kind of going downward on both sides. Like, you know, it'd have to be like this type of thing. If it's just this, you would need, you kind of need another side of it to be a hill, right? It's only one relative max, and it looks like it occurs at a y value of 4. At 4, and I guess I could say when x equals, it looks like x equals 0, huh? And then there are 2 relative mins, actually, and that's fine. There could be more than one relative max. There could be more than one relative min. There could be no relative max or no relative min. Like, they didn't ask us to do it, but in the previous example, this one, there's a relative min here because there's a low point, but there's no relative max because there's no hills. There's only a valley. So it's okay for there to be no relative max or no relative min. But there are 2 relative min that they occur at, let's see, maybe just get a different color for fun. These little valleys here, this guy and this guy. Looks like relative min at, the y values are 0 because they're on the x-axis when, there are 2 different x values though. It occurs at x equals -3 and x equals +3. So, because this is at -3, 0, this is at +3, 0. Alright, so yeah, those, you know, if you kind of memorized what the relative min is and they want the y value and all that, if you already know that, then it's not so bad. It's like, it's trying to keep track of what they want and how to write it. That's the hard part. Okay, so now let's talk about symmetry. So it says to test for y-axis symmetry here, okay. So, well, first of all, maybe we'll draw some pictures, let's see. Like y-axis symmetry, how would that look? That would be, you've probably seen parabolas before. You know, for example, let's draw this guy. Cute little parabola. That would have y-axis symmetry because this graph is a mirror image of itself across the y-axis. You know, if I were to flip the right side on top of the left side, it's a mirror image. And then, you know, x-axis symmetry is similar, but for the x-axis. So just, I mean, a simple one is like that. A parabola that's sideways, for example. Like that guy is symmetric with respect to the y-axis. Because if I were to flip that graph up and down, you know, it would be the exact same graph. Like, this is a mirror image of this, I guess, is the idea. And then the very last type of symmetry is origin symmetry, which is actually, it's hard to picture. Let's see, that one, an example of it would be like this is actually a graph of y equals x cubed, or I'm trying to make it look like that. That one you can tell it's origin symmetry because if you rotate 180 degrees, which is, you know, half circle, it's the same graph. So imagine, you know, if you rotate this blue graph that I drew 180 degrees, it'd be the same graph because the top half of it would land in the bottom half's portion, and the bottom half would land in the top half. So it's, you know, I think looking at a graph, it's kind of easy to tell if it has symmetry or not. But they're telling you how to mathematically tell if it has symmetry. If you don't have the graph in front of you, you just have the equation. So it says, first, to test for y-axis symmetry, replace x with negative x. If the result ends up being the same as the original equation, then it's symmetric with respect to the y-axis. Symmetry with respect to the x-axis is similar, but you're replacing y with negative y. And then origin symmetry, you're doing both. You replace x with negative x and y with negative y. So I guess you're looking for which variable, if replaced with a negative of itself, ends up being the exact same as it was before. And, you know, like in this example coming up, 3 part A, I can tell it's going to have some kind of symmetry because, for example, the square on the x, what's it called? That a square gets rid of a negative, right? So I think that'll be the same. But I'm supposed to test for all of them. I'm going to say y-axis symmetry. We'll test for that guy. They said to test for that, you're going to replace x with negative x. Okay. Oops, -1. So this is the one we were talking about. I'm pretty sure that, you know, nothing's going to change because the square gets rid of the negative. Yeah, this is the exact same thing. So it does have same as this guy, the original one. So it has y-axis symmetry. Which makes sense because actually this is the graph of a parabola. It's an upward-facing parabola, which we drew kind of in red up here. It should have a y-axis symmetry, you know. Okay. And let's test for the other types of symmetry, although I know they're probably not going to work. X. Sometimes they do, so don't, you know, this is just one I don't think will work. Symmetry. This time we were supposed to replace y with negative y, it says. So instead of, well, it started out like this, y equals x squared minus 1, but I'm going to write negative y. I mean, I guess you could write it in parentheses, but there's nothing really surrounding it that would necessitate not the negative, the parentheses. So that, and then there's nothing really that's going to get rid of that negative. That negative is just going to stay. There's nothing I can do with it. So since it's not the same as the original equation, because the original did not have a y. So no x-axis symmetry. Okay, then the last type of symmetry, origin symmetry, I test by putting a negative for x and for y. So let's see, I'm going to start out with the regular guy. It was y equals x squared minus 1, but where y was, I'm going to put a negative y, and where x was, I'm going to put a negative x. Alright, well, like we talked about before, the negative on the y isn't going anywhere, but the negative on the x does disappear. And now my job is to say, is this the exact same as the original equation? It is not, because there was no negative on the y. No origin symmetry, you know, for the same reasons as we stated here. It's not the same as the original. So let's try that with this next guy. So, okay, what do we do first? I just want to go in the same order. Y-axis symmetry? Yeah, let's try y-axis symmetry. Axis symmetry test. We're supposed to replace x with negative x. Let's see, y equals, we'll put a negative x where the x was, x cubed plus 5. But an odd power does not get rid of a negative. It just kind of pops it out in the front. You know, any even power, 2, 4, 6, 8, etc., would get rid of the negative. And there's nothing really I can do to simplify that, so I just compare that with the original. That's not the same as the original because there's a negative in front of the x cubed. Not the original equation, you know. I guess you're looking to see, is it untouched, or does it look untouched, like I didn't do anything to it. So no y-axis symmetry. Now let's try some other kind of symmetry. What was the other type of symmetry? X-axis symmetry. Hello. How did I forget that? X-axis. I just remember, you know, x-axis symmetry and y-axis symmetry, you test them by plugging in a negative for the opposite variable. So x-axis symmetry, I'd put a negative for y plus 5. Was x cubed plus 5? Yeah. And kind of like the last example, that negative isn't just going to go away. There's nothing that'll get rid of that negative. You know, there's no absolute value. There's no second power. There's nothing that would get rid of it, so, you know, there's nothing really I can do. That's it. That means there's no x-axis symmetry, because that's not the same as the original. Alright, now we'll try origin symmetry, hoping for the best. You know, and it's not every function has symmetry. Sometimes functions have more than one symmetry, like I can think of a function that has x and y-axis symmetry and origin symmetry maybe. There's some functions that only have one of the three, and some have none of the three. So I guess don't expect to see a yes for one of these necessarily. But let's see, origin symmetry, that's where we're supposed to take x and y and replace them with the negatives. So I'll put a negative for y and a negative for x. There we go, and see what happens. Well, this negative doesn't go away, and this cube just pops the negative out in the front like we saw in the y-axis symmetry test. So this definitely doesn't look like the original. Sometimes you can play around with it, like, you know, I notice, well, this guy has a negative, this guy has a negative. What if I try to divide the equation by -1 to get rid of those? Then maybe it'll look like the original? Maybe. Sometimes that works. By -1. Let's see. So that all that does really is change all the signs, right? So then it'll be a positive y, a positive x cubed, but if I divide by -1, the 5 becomes negative. So although the y and the x cubed look good, they look more like the original. The 5 is supposed to be a positive to begin with, so nope. This is not the same as the original, whether I look at this version of it or that version of it. So it doesn't have origin symmetry either. This guy is not symmetric at all as the original. So no origin symmetry. Alright, that's a bummer. Oh well, what are you going to do? So let's try this one. I think this one might have some kind of symmetry. Let's see. If I do y-axis, I'm just going to do this one quicker because now I think we get the hang of it. Y-axis symmetry, I'm replacing x with -1. Oh, sorry, negative x. But that negative doesn't disappear. So it's a no. No y-axis symmetry. What about x-axis symmetry? That's where I replace y with -y. And again, similarly to the y-axis symmetry for this one, since it's an odd power on y, that negative's not going anywhere. And that's not the original. But maybe origin symmetry will work. Origin, okay. That's where I replace y with -y and x with -x. Well, like we saw before, the negative here is not going anywhere, the negative here is not going anywhere. But I can manipulate this by, you know, adding what I want to both sides, multiplying what I want to both sides. I'm going to multiply or divide both sides by -1 and see what happens. Because it's the same equation, it just looks a little different when I do that. So it looks like that is the original equation. So this is a yes. There is origin symmetry. Same as the original. So I guess keep that in mind, just because if you plug a negative in and it looks different than the original, try to see what you can do to it to make it look more like the original. You know, multiply both sides by something, divide both sides by something, add something. If it's possible, then it could have that symmetry and it might not look like it does. Let's try this guy. This guy, we're looking for first y-axis symmetry. I'm supposed to replace x with -x. Oops. There we go. Y squared. Well, the square on the x is going to get rid of the negative, so it looks like it is the same as the original. Yes, there is x or y-axis symmetry. That's good. Okay, let's look at x-axis symmetry. That's where I replace y with -y. And I think something similar is going to happen because the square on the y is going to make the negative disappear. And that equation is also the same as the original, so it's yes, it has both x-axis and y-axis symmetry. Origin. Let's try origin. I almost feel like I'm getting greedy now. Like it had one kind of symmetry, had another. Come on. I'm trying to get a third too, really? Alright, this is where we're supposed to replace the y and the x with a negative x and a negative y. So, well, since x and y have squares on them, they're getting rid of their negatives. And that also is the same as the original. So it's a yes. Interesting. So that one, I don't know, in case you're curious, like what the heck kind of graph would have x-axis symmetry, y-axis symmetry, and origin symmetry? This guy's graph, which we'll see pretty soon, probably in this class, or next semester, maybe if we don't get to it, is a circle. This is a circle of radius 10. So of course this makes sense. It's a circle if you were to, I guess, rotate it 180 degrees, of course it's the same graph. That's origin symmetry. If you flip it across the y-axis, it's the same. So that's y-axis symmetry. You know, x-axis similarly for the x-axis. That's why it had so much symmetry. Okay, and let's see these guys. Okay, so these ones, they're just, this example is kind of pointing out that they give special names to y-axis symmetry functions and x-axis symmetry functions. Like it says here in the note, we call a function even if it has y-axis symmetry. We call a function odd if it has origin symmetry. X-axis symmetry, there's no real special name for it. I'm not sure why. I think because if you have x-axis symmetry, you're probably not a function. So we don't really care about you anyway. We only want to look at functions, usually. So I think that's why. But let's see, we can look at these, and I think since we already did the testing for x-axis, y-axis symmetry, we can probably go through these pretty quickly. But one thing you might want to do is replace f of x with y, just so you remember. But this guy is going to have y-axis symmetry, but no origin symmetry. Y-axis symmetry. And you can test it the exact same way you did before. No origin symmetry. So it's even, because even is y-axis symmetry, not odd, because odd is origin symmetry, and we already decided that it doesn't have origin symmetry. Let's see, and here's 4b. This guy would, well, you know, this one's a little more complicated. Maybe we'll actually try this one. So we want to test for y-axis symmetry. Let's see. I'm going to put a negative in for both x's. Yeah, I think we haven't seen one where there's a negative, or sorry, there's more than one x. So let's see, the cube on the x would not get rid of the negative. And then this x is still negative. Oh, I forgot to replace the y with a negative y. Hello. Sorry. Because we're looking for origin symmetry. Oh wait, what? No. Oh my god, we're not doing that yet. Sorry. We're doing y-axis symmetry right now. Hello. But that is not the same as the original. Not. Because both x's became negative. And the y is not negative, so I couldn't, you know, if I try to divide the whole thing by -1, that's not going to work. Okay, so it's not even. Because even would mean y-axis symmetry. But it is odd. Because if I replace the y with -y and the x with -x, then everybody's now the opposite sign of what it was before, which means I should be able to divide the whole thing by -1, or multiply by -1, whatever. Everybody's sign will change and it'll be back to the original. So it is odd, not even. Let's see, this guy I think would be similar. You know, if you, let's see, I'm going to replace g of x with, what's it called? With y first of all. If I replace the x's with -x. Oh wait, this is a 4, sorry. 4. And these are both even powers, so I'm going to get positives where those negatives were. And this is the same as the original, so it is even. Same as original. Let's test for odd. Is it odd? We're going to put a -y where the y was, and a -x where the x was. Well, the y will stay negative, but the x's go back to what they used to look like. But so it's like here, the equation's almost the same as the original, but the y is negative. I mean, the right side looks good, the left side looks bad. that means it's not odd. Even if there's one thing off, if everything looks good except one little thing, that's still not right. Okay, let's see. We'll try this guy now. Y equals x to the 5th plus 4. Let's test for even symmetry. That's the same thing as y-axis symmetry, so I'm going to replace the x with negative x. Alright, but because if this was an even power, that negative would go away and it would be even. Which now you can probably see why they call it even. But since it's an odd power, the negative doesn't go away. And this is not the same as the original, and even if I try to multiply or divide by -1, it'll still look different from the original. So this guy's not even. What about odd? Let's try that. That's where I replace the y with -y and the x with -x. Okay, so this guy's negative. The 5th power keeps the x negative. So it's almost like everything changed signs except this 4. So even if I were to take this and divide the whole thing by -1 like we've tried before, it kind of looks like the original guy, but this 4 would become a negative, so this is not odd either, because there's one thing that looks different. Okay. Oh well, you never know. Okay, now these are piecewise functions, we call them. So these, you'll see these a lot more in the next semester, so this is more of a taste. So if you really don't 100% understand this, it's normal. That's how I felt when I learned this. I did not get it at all. Okay, what this is like a Frankenstein. You ever seen that movie or heard of it? Actually, I don't even know how to spell it. Is it like that? Frankenstein. You know that guy, he's supposed to be like a person that they took an arm from this guy and a leg from that guy and a head from this part and they put it all together into one dude. That's what this is like. It's like 2 different lines that they took and shoved together and made one function. So like, okay, they kind of break it down. This is talking about one line here. The line looks like y equals whatever this is on here, 3 for x values, like it says in the inequality there that I've boxed. For x is less than or equal to -1. So where's that? X is less than or equal to -1. That's, maybe I'll try to highlight it here. On the axis. Here's -1 on the x-axis, and then less than or equal to is that way. So in that area, I want my line to look like y equals 3. And if you remember, y equals 3 is a, what's it called? A horizontal line. So I'm starting there, going off in this direction. I want my line to look like that. But that's only for that highlighted portion of the x-axis. The other part of the x-axis is, what's it called? Is described down here. They want it to look like y equals whatever is on the left side of that, x minus 2, 4. And then they specify the x values they want it to look like. X greater than -1. So let's see, x greater than -1 is kind of the opposite side of the x-axis, from -1 on this way. So on that side, I want a different line to kind of be visible. I want it to look like y equals x minus 2. So it's like you're graphing that line, y equals x minus 2, but you're only trying to draw it on half of the xy coordinate system, because half of it looks like a different line. So let's see, y equals x minus 2. If I were to use the slope and y-intercept, the y-intercept is -2, so here I start here, and then the slope is 1. So I'm going to rise 1 and run 1 from that point, which would land me here. But I got to remember that that only extends on the x... Oh, I went too far. Oh well. That only extends on the x-axis for this highlighted blue part. But once I get to this guy, for example, I don't want to cross that, because notice that it says x is greater than -1. Strictly greater than, that means I don't want there to be a point here. I did put a point up here. That's because it said x is less than or equal to. So look out for the equal to part. Yeah. So that kind of looks like, it looks like they took 2 lines and shoved them into the same graph, you know, like for example, maybe this is me going too far, but it's like they took, okay, here's 2 different graphs, okay, blah, blah, blah. I'm gonna first draw a horizontal line, say it's at y equals 3, okay, da-da-da. And then there's one cute line. Where's the other cute line? He's like, da-da-da-da-da. That's y equals x minus 2, and this is y equals 3, this little guy. It's like I said, you know, I like both of these graphs, but I kind of like the left side of this one and the right side of that one. What if I were to take the parts I like and shove them into the same graph? That's kind of what it feels like, but that's what these piecewise guys act like. Well, let's try another one just to get the hang of it. So this portion will describe one line. I want it to look like y equals 2x And then they're going to specify where they want that. They only want it for x values that are less than 2. So see, x values less than 2 are like from here on to the left. Less than, yeah. So I'm gonna graph that line. That has a y-intercept of 0, so it'll start at 0. Then it has a slope of 2 over 1. I'm going to rise 2 and run 1. And that goes off to the left forever. But then when I start extending it to the right, it should stop at this value here. X is less than 2. So once I get to 2, I better put an open circle. Okay, so let me, maybe just to help. It's kind of like these numbers here should be the same. This saying on one side of -1, it should look like this. On the other side of -1, it should look like that. So it's kind of describing it, yeah, on the left and the right. So here it's saying the graph that I want is going to look like one thing on the left of +2 and something else on the right. So it's almost like you can draw a little barrier here. Remind yourself, hey, I'm trying to draw two different graphs, and this is where one ends and the next one begins, sort of. I think that kind of helps me. And then you should probably erase that line, that yellow line I just drew, when you're done with your graph, because that's not really part of your answer. That's just helping guide you. Okay, so we got half of it done, and then the other half should look like y equals -1/3 x plus 1, and that's for x greater than or equal to 2. Okay, that's actually tricky because, when I see the equation of this line, I want to say, okay, the y-intercept is 1, and then the slope is 1/3, or -1/3, so I'm going to rise 1, run 3. But that would only work if I was including the y-axis in this. But remember, it says, I want this only for x is greater than or equal to 2. I'm only allowed to draw, I'm only allowed to draw on this side of the yellow line, which means I can't touch the y-axis. The y-axis is already spoken for with the red portion of the line. So actually I'm not able to use the slope and y-intercept, like I said, because that would mean I'm going to draw on the y-axis, but I can't because I can't cross this yellow line. So the only thing I can do is maybe make a table of values. But remember, for a line, all you really need is 2 points. They used to tell us 3 just because they thought we were going to make a mistake, But I just got to make sure the values I pick are on the right side of that yellow line. And I think I kind of, also I want to be strategic because I see the equation I'm having to plug it into, this guy. I'm going to have to multiply whatever x value I choose by 1/3. So I think, okay, what kind of x values are nice to multiply by 1/3? I think, multiples of 3, like 3 is okay, 6 is okay. That might work, so let's try that. I'm going to go, it's supposed to be y equals -1/3 times x, but here I'm plugging in a 3. And was it +1? Yeah, +1. So it's y equals, let's see, -1/3 times 3 is -1. +1 would be 0. Okay, so there's 1 point. And then the other point, I'm going to try to do the same thing, but I'm putting -6 in, or sorry, +6 in. So -1/3 times 6, that would make -2. +1 would make -1. Alright, so that should be all I need, is those 2 points. 3, 0 would be here. And then I have 6, -1 would be here. Alright, I'm going to connect those dots and draw a line, but I cannot cross that yellow line. So I'm going to go to this guy. But this time I'm actually going to make a filled in circle on on the yellow line, which is the border, because the cutoff point here was, we're saying x is greater than or equal to 2 for this line. For the green line, I can be equal to 2, but for the red line, I have to be strictly less than, and that's why we put an open circle. So these take some getting used to for sure. They're very tricky. But like I said, I think in this class, it's more of an intro so that in the next class, it'll be easier. I don't think we really expect everyone to 100% understand that. It's just a very tricky concept. But like I said, just do your best. Don't worry about it too much. And we'll kind of talk about it more next semester. Okay, so the last topic in this this section is what they call the difference quotient, which this is another concept I think we talked about in the last section. There's something we went over where I said, you're just kind of doing this and you don't really know why. And we don't really explain why, but you'll see in coming classes why. So this is actually, yeah, like it says here, this will be important in calculus. Right now it means nothing to us. We don't know what the hell we're doing. And it's hard to trust that it's important later and you don't really care right now. But I think once you get to it in calculus, it'll be easier because you've seen it before. So that's the good news. We're supposed to calculate this crazy fraction thing here. It's supposed to be f of x plus h minus f of x over h. And you might be thinking, well, I've seen f of x before, so that's interesting, okay, but what the hell is h? That's kind of the question. What the hell is h? Well, you'll find out when you take calculus. That's the answer. Right now it means nothing. It'll represent something in calculus, but okay. So let's see. For this example, 6a, we have a specific function. We have f of x is negative 2x squared plus x plus 5. They want us to calculate the difference quotient, which means they want us to calculate that quantity up there, f of x plus h minus f of x over h. All right, so for me, that's kind of a complicated looking thing. So usually what I do is I first calculate, let's see, actually, I'll just keep this color. Okay, first, calculate the one part of the difference quotient that looks weird and complicated, the f of x plus h. So I think if you just focus on that first, and then once you figure that out and simplify it, then bring it together with the whole difference quotient, that makes it a lot easier. So, okay, this kind of goes back to, I think in the last section, how we plugged in, we were substituting things into functions, like we found f of negative 5, which is normal, but then we found f of x plus 3 or something weird. So I think that's what we were doing. We were trying to practice for this thing. But remember, if I calculate something like f of x plus h, that means I'm going to try to, let's see, I'm going to try to look at the right side of the function, but where the x's were, I'm going to replace it with x plus h, because that's what's in parentheses. So I'm going to rewrite everything else the same, negative 2, something squared, plus something plus 5. Let's see, I didn't really extend the highlight far enough. Okay, there we go. But where the x was, I want to put what they put in parentheses, x plus h. And it just seems so weird and so bizarre, but that's, the higher you go in math, the weirder it gets. Like this, what the hell are we doing here? Oh, Lord. The higher you go in math, too, you stop questioning it because you don't really care why anymore. You're just like, oh my God, get me out of here. Just kidding. But let's see, that means, this looks a lot, pretty familiar. In the previous section, we did something a lot like this. If I'm squaring x plus h, that means I'm writing it twice. So I might kind of focus on that first, and then I have to FOIL that out. Ugh. X times x is x squared. X times h, I guess, is like hx or xh, whatever. And then another h times x, hx. Those will be like terms. So, and then a h times a h is h squared. All right, then I guess I could bring this down too, huh? X plus h was in parentheses, but there was really no reason for it because there was nothing to distribute or anything like that. And now the next thing to do would be distribute this. Oh, no. I'm going to combine the like terms that are in the parentheses. There are two hx's, so it's like I can write 2hx. Or xh, whatever you want to call it. H plus, there we go. Alright, now I'll distribute the 2. It'll become, or negative 2. Negative 2x squared minus 4hx minus 2h squared. And then the stuff that was outside the parentheses plus x plus h plus 5. And then we don't have any like terms, do we? I don't think. Nope. X squared, hx, h squared, xh. Yeah. These are all separate terms, so okay. So now we're trying to calculate, remember that was just f of x plus h. Now we're going to actually calculate the difference quotient, which is f of x plus h minus f of x all over h. Okay. So this, at least the, maybe I'll try to highlight so we can see what's going on. This was what we just calculated. That was just this portion, f of x plus h. So I'm going to write that first. Let's see. Negative 2x squared minus 4hx minus 2h squared plus x plus h plus 5. So it's supposed to be that. Maybe I'll put it in parentheses just to make it more clear. Minus, okay. And then f of x, that's, here he is, the f of x. That's just the original function itself that was given. So I'm just going to, kind of rewrite that. Negative 2x squared plus 5, plus x plus 5. But I should, just to be careful, I should put it in parentheses. Because the subtraction sign between f of x plus h and f of x is supposed to be for every term in here. So I'm going to have to distribute it when when I get when I get the chance. And that's all over h just because that's just, it's kind of just the way it goes. So maybe I'll highlight the parts of what I just wrote that are correlated to the, dang it. That was not supposed to be blue, that was supposed to be yellow, sorry. Yellow. And the other guy was blue. There we go. All right. And now I think if we distribute the negative sign into the parentheses, there'll be some like terms. What do we have? I'm going to rewrite. Well, these parentheses don't really need to be there. You know, there's nothing really to distribute or anything like that. So I'm just going to remove those ones. Write all these crazy terms. But when I distribute this negative in here, it'll change all their signs. It'll become positive 2x squared minus x minus 5. And that's all over h. So let's see, now what's left? We have... And this is a point where a lot of things should cancel. If you did it right, there should be a lot of terms that just disappear. So for example, the negative 2x squared and the 2x squared cancel. The plus x and the minus x cancel. The plus 5 and the minus 5 cancel. So let's see, now I'm just kind of looking at what's left here. Everything that's left should have an h attached. 4hx minus 2h squared. I think that was it, huh? That's all that's left on the top? Yeah. All over h. Okay, now I should be able to... At this point, okay, I guess that's the idea. All terms left... This is just kind of a hint that should help you in your problems when you get to them. Should contain h. Okay. So now what you're going to do is factor h out of the numerator and cancel it with the denominator. Numerator. And that should be, you're done. And cancel with denominator. Okay. That's the idea. That's how all these should go. It's, you know, I think once you do a few of these, you'll get the hang of it. But let's see. I'm going to factor an h out of the numerator. Negative 4x minus 2h would be left. And then, of course, the h in the denominator is just sitting there waiting to see what happens. But now the h that I factored out and the denominator itself cancel outright. And only what was in the parentheses is left. And that's your answer. And like I said, right now that has no meaning whatsoever. But when you take calculus, it will. Alright, so I think we're going to do that again, but we're going to try to go a little faster now. But like we did in the previous one, we're going to calculate f of x plus h first. That's where I take the x squared, replace it with x plus h, take the x, replace it with x plus h, and then we'll see what happens. Let's see, we have to write x plus h twice, and FOIL, I'll do that, and then I'll also distribute this 4 in, negative 4, making it negative 4x minus 4h plus 3. Okay, and when I FOIL this x plus h times x plus h out, I get x squared plus hx plus hx plus h squared, and then the terms that I already had at the end. Those hx's are like terms, so it should be x squared plus 2hx plus h squared, now minus 4x minus 4h plus 3. And like the last one, none of those are like terms, which is kind of a bummer. But now we can finally put that together. And what we're trying to, the whole thing we're trying to calculate, the difference quotient. That's f of x plus h minus f of x over h. So let's see, maybe we'll, like we said, we'll highlight what we're plugging in here. F of x plus h, that's what we just calculated, so I'll put that first. That's going to go here. You know what, and I better separate this from the previous problem so we don't get confused. Get away from me. Okay, there we go. So it should be the x squared plus 2hx plus h squared minus 4x minus 4h plus 3. That's just the first portion, and then there's, excuse me, a subtraction sign, and then the f of x, okay, let's see, f of x, but that's always just the original function, because that was given. I'm just going to now write x squared minus 4x plus 3 in parentheses. Make sure you put it in parentheses, because you'll probably forget to distribute the negative or the subtraction sign if you don't. X squared minus 4x plus 3 over h. Alright. So now, just like the previous one, what I've highlighted in yellow doesn't really need to be in parentheses. I guess I just want to be fair to what's in blue. Because he'll feel, you know, he'll feel left out if he had to be highlighted and no one, or no, he had to be in parentheses and no one else did. But these guys need the negative sign or the subtraction sign, making all their signs change. Negative x squared plus 4x minus 3. And that's all over h. And like I said, at this point, a lot of stuff should cancel, leaving you with only things that have an h attached. So, for example, this guy in the front, x squared cancels with this minus x squared. The negative 4x here cancels with this 4x. And this plus 3 cancels with that minus 3. So what's left? 2hx oops, plus h squared. And then sometimes I forget a term, like this guy, he was kind of hiding, but I don't want to forget him. Minus 4h, but I think that's everybody, all over h. Okay, now if I factor an h out like we talked about in the numerator, 2x plus h minus 4 is left over h. And now that I factored that h out, it should cancel with the denominator's h. So I'll just be left with 2x plus h minus 4 is my answer. Yeah, I'm sorry, I know that's meaningless right now, but someday it'll make sense if you take calculus. Well, hopefully that made some sense. Those are, the last two concepts were really difficult, so I think this last one is another one that we were talking about where they just want to introduce this now to make it easier later. But we don't really expect you to 100% understand it now. It's just, I think it's good practice, the algebra part of it, and then, yeah, just in the future it'll make it easier. But really don't feel bad if you don't 100% understand it right now. I sure as hell did not. But, okay. Thank you for listening. I'll see you in the next video.